So in this video, I'm going to introduce some properties of definite integrals, and then we're going to apply those properties to a given picture to find the definite integral that's given. So the first property is I have f of x dx, where we go from a to a. Well, that's kind of weird, right? So what's going on? If we sum up all the rectangles from A to A, well, A is a single point, right? So if you think about the picture here, typically it's from A to B, right? And then we find all of the area in here. Well, what's the problem? Now we have no B, right? Oh, I messed up. Okay, let me try this again. I'm gonna make one. There you go. Okay, so if you're finding this integral, that's the integral from a to b of f of x dx, typically. However, from a to a, that means that a and b are the same, right? So what would happen here is you move this b all the way over here. And so now you're just trying to find the area of just this single line right here. So what do we know about the area at a point? At a single point, there is no area, and so this is equal to 0. So if you ever see a hard integral, but then the bounds, the limits of integration go from a to a, then you don't even have to do any math. The answer is just 0. Okay, pretty cool trick. Now, another property, we take the integral from a to b, and then we add to the integral from b to c. Okay, and what is this equal to? Well, this equals to the integral from a to c. Okay, so what's going on here? This is like how 5 plus 3 equals 8, right? So here's the idea. So we've got some curve here, and it's from A to B to C. And so what this says is, if I take this integral, this definite integral, and I get that area there, and I take this integral here, and I get that area there, then this is the same as if I add up everything from A to C, okay? That's the idea. Basically, this allows us to take any integral we have and break it up into pieces. All right, very powerful for us to be able to break up an integral into pieces so we can evaluate the different pieces individually. Why is that powerful? Because whenever you have pieces that are positive and pieces that are negative, it's good for us to break them up into those corresponding positive and negative pieces. Okay. Another property, if I have f of x dx integrated from 0 or from a to b here, then what do I know? Well, from earlier video, we know that height is equal to the function value minus the y equals 0 line, okay? And that the delta x, the dx, is the right minus the left endpoint on the base of the rectangle. If we go back to here, you can see that from the picture. You have your f function here and your y equal to 0 line here. So the base and the top, so the top minus the bottom is f minus 0. So top minus bottom. And then the width of the rectangle, to find the width, I take the right side and I subtract it from the left side value. If this were 5 and that were 3, then the width there would be 5 minus 3, which gets you 2. Okay? So that's right minus left. Now, that is a positive number when you do right minus left. However, say instead of having it integrate from A to B, we swap it around to where it's integrating from B to A. Now, all of a sudden, this becomes negative. So to make it equal, we do negative and a negative, make it positive. So if you switch the bounds, you better put a negative out front, okay? Because what we're saying here is the function stays the same. However, the dx changes from left to right, which picks up that negative sign there. Okay? So just in general, if I have f of x from a to b, and I want to switch the limits of integration to be from b to a, then I need to put a negative sign out front. Okay? This rule here, this rule says that if I have the integral of the sum of functions, or the difference, plus or minus, then that's equal to the integral of the first function plus or minus the integral of the second function. Okay? So plus or minus depending on what symbol is put into that. Okay? Now, number 5 says that I have a constant inside my integrand here. So k times f of x. Then what can I do with the constant? I can pull the constant out front. Okay? So the constant multiple rule works for definite integrals as well. All right, so now let's apply these properties from definite integrals to a problem. So we've got a graph of a function f of x given, and I want to use geometry, so geometric formulas that help me find area to calculate the definite integrals given. So the first definite integral I want to calculate is the integral from -3 to -1. So I'm going to change colors here to make this more visible. So from -3 to -1. So x equal -3 is here to -1. So it looks like this shape, this geometric shape here, is a triangle. So this is area of a triangle. Now, area of a triangle from geometry is 1/2 base times height. You're having trouble remembering your area formulas, go look at the reference sheet. It's got a bunch of area formulas for you. So I'm finding that area here. But what do I know? This is below the x-axis. So since it's under the x-axis, what do I know about area under the x-axis? Well, I know that area under the x-axis is absolutely negative. So I'm going to put a negative sign there. And so I have -1/2 times the base. Well, what is the base? How long is the base? It looks like it's 2. And then the height, looks like the height is 1, 2, 3. Okay, I can look at that at the point there. I can see those points and figure out that information. So -1/2 times 2 times 3 gets me -3 for the definite integral here. Okay, so I'm using geometry to help me find these definite integrals. Now, for this next one, I have f of x from -1 to 5. So -1 to 5. So -1 is here, and then +5 is here. So I want the area under the curve here. Okay, area under the curve here. Now, you've got technically what's going on here, this vertical line here makes it where it's not a function, but we still have this area, right? And so even if the function went off like this, we're stopping at that x equal to 5, and we started at that x equal to -1 here, okay? So with this picture, I'm trying to find the area. This shape is a trapezoid. So it has parallel bases, 2 parallel bases, okay? And then it has this height that connects the 2 there. So the formula for area of a trapezoid is 1/2 base 1 plus base 2. Basically, you're averaging these 2 bases, and then you multiply by the height, h. Okay, since it's above the x-axis, I'm dealing with a positive formula now. Okay, so I'm dealing with the positive formula. And so whenever I plug these numbers in, the height here is 1, 2, 3. Okay, so the h is 3. Base 1 is 6. 1, 2, 3, 4, 5, 6. and base 2 is 1, 2, 3, 4. Okay? Multiply this out, I have a half times 10, which is 5, times 3 is 15. And so my area of this trapezoid here is equal to 15. The area of this triangle here that we just found is -3. Okay? This negative because it's below the x-axis, and then this is positive because it's above the x-axis. Now I want to find the area from -3 to 5. So from -3 to 5 here. Well, we just talked about this. This part here is positive area, and this part here is negative area. So since I'm switching from positive to negative, I'm crossing that x-axis here. I need to break this integral up using my splitting up rule here, right? So I took one integral and I split it into two integrals. So I'm going to do that here. I'm going to break it up into a positive part and a negative part. So the first part goes from -3 to -1. So -3 to -1. And the area of a triangle under the x-axis is negative. We've already got that area. And then the second part is the part from -1 to 5. And so -1 to 5 is the trapezoid, which is above the x-axis from -1 to 5. We're above the x-axis. From -3 to 1, we're below the x-axis, right? So if I'm sticking with my colors, you can see there. Okay. Now, I want to find that total area from -3 to 5. That's what I'm looking for. So to find that total area, I'm going to take the answer from the first part, -3. Okay, that was the area of this triangle under the curve, plus the second part, 15, which is the area above the curve here. And so whenever I add those two together, what do I get? I get -3 plus 15, which gets me 12. Next one, number 4. This is going to be integral from 8 to 8 of f of x. Well, what is 8? Where's 8 at? 8 is right here. So integral from 8 to 8. So I didn't have to even move that. Oh my goodness. What did we say whenever we were trying to find the area of a line at a single point that has no width? Look, guys, if there's no width here, you think about the area of one rectangle. Look, it's the height, right? Base times height. Well, if the base of the rectangle has no width, then that means the base is equal to 0. So who cares what the height is, what that f of x is, whenever the base is equal to 0? Because the result, when I multiply 0 times whatever number you get, is going to give you 0. So anytime you see integral from a number to that same number, automatically it's 0. So don't let that trick you. Okay, this last one here, this last one is the integral from from 11 to 5. 11 to 5. Oh my goodness, look. This is weird because up to this point, everything that we have done has had from a number that's lower to a number that's bigger. A number that's lower to a number that's bigger. Lower to bigger, right? And then the same thing and the same thing there. So this is the other oddball case. We start with the big number, and then we're summing our rectangles backwards here. So remember when we talked about this rule here where we swapped, instead of going from right to left for our delta x, we were going from left to right, and what it caused was that negative sign to come out in front. So we need to fix this. So this is equal to the integral from, instead of 5 being the end, we make 5 the beginning. to 11 so that we have from least to greatest, right? Summing from least to greatest. But if I do that, I have to pick up that negative. Okay, so this is that rule right here in practice. So we literally, if your lower bound is bigger than your upper bound, then you need to flip those around, okay? And when you do, you have the negative come out in front when you interchange the limits of integration. And so whenever I do this, now I need to find the area from x equal 5 to x equal 11. Well, it turns out I'm going to use blue here because this area is below the x-axis. So that means I know it's going to be negative, right? But there's a little trick that's kind of going on here, okay? So this is a semicircle. So area of a half circle, and the area is under the x-axis. So not only is my area going to be negative, but it's half of a circle. So I do 1/2 pi r squared, okay? And it's negative 1/2 because it's under the x-axis. But see, I told you that this one was a little bit tricky because what's happening? Negative, negative make a positive, right? But what else do I know? Well, r here, the radius, happens to be, looks like the radius is 1, 2, 3 here, okay? So my radius is 3. If you didn't know, it's a diameter of 6, so that means that the radius has to be half of that, so the radius is 3 there. And so r squared, I put a 3 in there, and so that reduces to 9 pi over 2, okay? Now, what happened? Because didn't we say that this area was supposed to be negative? Well, it is negative, but what did we do? We asked for the limits from sum from 11 to 5. And because we did from 11 to 5, that caused our answer to become the negative of 5 to 11. So we have this double negatives action going on here that causes it to actually turn into be a positive here, okay? So a little tricky on that last one, but let me zoom out so you can see all of those problems. And so you saw the properties here, and then you saw the properties in action here.